Video 2 of integration practice. We worked integrals 8 through 14. Number 8. Oh, I really like this question because in particular, we can approach it more than one way. So I would approach this using substitution, but it's a little clever of a substitution. Let's see, we can take u to be x plus 1, and then du is dx. Well, what I need to do is convert every piece of my integral to something of u, as we know. So this part, we have square root u du, no problem. But then I have this x in front. The good news is, with this substitution, we can solve for x. So note that x equals u minus 1. Now, my integral becomes u minus 1 times u to the 1/2 du. This we can integrate. I need to write each term as a power. I have u to the 3/2 minus u to the 1/2 du. We add a power, u to the 5/2, divide by the higher power. Here we add a power, u to the 3/2, divide by the higher power, and then we put plus c. Okay, at this point, I need to go back to x. Really, at the same time, I don't like to leave fractions in my denominator. So this would be 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. And this is my final answer. You will notice this was integration by substitution. So much fun. Now, is this the only way to do this problem? Well, no, it is not. I was going to stop here. We have a final answer. However, we're trying to practice integration here, and so I will illustrate another technique. We can use integration by parts. So in this case, it might be more challenging to pick the u using Lyautey, but we can still pick the u for integration by parts. The idea is you want something that gets simpler when you differentiate. That's the way I think about it. Oh, and so we would want to choose u is x. The reason I am doing this, or one way you might even think about integration by parts, is we do see a product here. Okay, so then dv is everything else, including the dx. Now we can differentiate. And we can integrate. So here, in fact, we've already integrated a 1/2 power above. We get 2/3 x plus 1 to the 3/2. All right. So integration by parts goes uv minus the integral of v du. Let's write it down. We have 2/3 x plus 1 to the 3/2 minus the integral of 2/3 x plus 1 to the 3/2 dx. Okay, so we have 2/3 x plus 1 to the 3/2. And then we're going to have 2/3 really times 2/5 x plus 1 to the 5/2 plus c. Now, all we can really do here is write this coefficient, 2/3 times 2/5 as 4/15, which for spacing reasons, I will just change here like this. Here's my final answer. Now, they look different, but this comes from the nature in which we calculated the antiderivatives. You can plot them. You will find they are the same. Number 9, we have some different approaches for this one as well. I think I will only work this question one time. So one thing you could do would be a clever substitution, just like here in 8. You could long divide. We have polynomial divided by polynomial. I think I'm just going to rewrite it. So note that y is y minus 7 plus 7. Definitely true. So I'm going to factor out the 5. I usually don't in definite integrals because sometimes I forget to put it back. But if you factor a constant out, just don't forget it at the end. So we have y minus 7 divided by y minus 7 plus 7 divided by y minus 7. The first is 1, and the second, I can just rewrite it. We have 7 divided by y minus 7. Now this is something that I can integrate quite quickly. We have the 5. We integrate 1, we have y. We integrate the second term, we get 7 ln absolute value y minus 7. And then we want to evaluate all of this between 0 and 4. This is a definite integral here. So we have 4 plus 7 ln 3, and then subtract off 7 ln 7. Altogether, we get 20 plus 35 natural log of 3 over 7. You don't have to use a log property to simplify here, but I did. So here's a final answer. Very nice. Number 10. Okay, we have a sum of 2 terms. So let's write this as a sum of 2 terms. We have the integral 1 over cosine squared plus sine x over cosine squared dx. You see, the first term we know how to integrate. 1 over cosine squared is the secant squared. Maybe I will do this though. Write it as the secant squared. The second term, I hope you're thinking what I'm thinking, which is substitution. In fact, we can even write the cosine x in parentheses to see it. So just for the second integral, we let u be the cosine of x, and then du is negative sine x dx. Handed to me in my integral, well, we have sine x dx, which is minus 1 du. This substitution box, as I mentioned, is just for the second integral. The first one, we can go ahead and integrate. The derivative of tangent is secant squared. Okay, then we have an integral. It's going to be u to the minus 2 times minus 1 du. Okay, we have the tangent once again. This is a power rule. Oh, I have a negative sign. So we have minus u to the minus 1 over minus 1 plus c. Finally, we go back to x, really just in the second term. So we have the tangent of x plus 1 over the cosine plus c. I like this question. Next one, it looks intricate. It will actually be quite short once we convert to an integral of u. So this is substitution, and it is definite. Let's get started. We see inside the parentheses, we have e to the x minus 1. du is e to the x dx. Okay, wonderful. We have exactly du in our integral. Now, definite integral with substitution, I'm going to change my limits of integration to be u limits of integration. Then I don't have to go back to x. So when x equals 0, we have u is e to the 0 minus 1, which is 0. When x is natural log 3, u is e to the ln 3 minus 1, which is 3 minus 1, or 2. Okay. So we have an integral. U ranges from 0 to 2. And then we have u to the 5th du. Now, how nice is this? We had this integral that started off quite complicated looking, and we're just integrating u to the 5th du. So we have u to the 6th over 6, and we evaluate between 0 and 2. At this point, this integral is not too bad. Okay, 2 to the 6th over 6 is the same as 2 to the 5th over 3. So we have 32 over 3. And then subtract off the lower limit of integration, which just gives us 0. So this is my final answer, 32 over 3. Number 12, polynomial divided by polynomial. Here, though, the degree of the numerator and denominator are the same. We can do a trick similar to what we did a few integrals ago. We can write x squared as x squared minus 9 plus 9. So 2x squared, I'm just going to multiply by 2 everywhere, would be 2x squared minus 9 over x squared minus 9, and then plus 18 over x squared minus 9, right? Okay, this is not a tan inverse. We must use partial fractions. So we have 18 divided by, we can factor x minus 3, x plus 3. Okay, general form of this partial fraction decomposition. We have two distinct linear terms. We're going to have a over x minus 3 plus b over x plus 3. Now, in order to get a common denominator here, we multiply this one by x plus 3 divided by x plus 3. We multiply this one by x minus 3 over x minus 3. Let's write my equation. Maybe I'll do this in black. We will have 18 equals a x plus 3 plus b x minus 3. Now, I always regroup things. So we have 18 equals, well, we have x times a plus b, and then we have the constant is 3a minus 3b. We really have a system of two equations and two unknowns. We can write it underneath. First of all, coefficient in front of x must match the coefficient in front of x on the other side. So a plus b equals 0. And then the constant has to equal the constant on the other side. 3a minus 3b is 18. What we can do here, we can take the first one, multiply by 3, and add. We will get 6a equals 18. And so a is 3. Okay, very quickly after this, you can see, just look at your first equation. B will be minus 3. All right, so maybe I will underline these in highlighter. We have our coefficients. Now let's get back to our integral. We have an integral. The first term is 2. Then we have plus 3 over x minus 3. And then minus 3 over x plus 3. At this point, oh, we are in such wonderful shape. We can integrate each term. So we have 2x. We have plus 3, ln absolute value x minus 3, minus 3, ln absolute value of x plus 3, plus c. Final answer. This was partial fractions. 13, we have another definite integral. I will use substitution. Why? Well, you see, I have this function up inside the exponent of e, and I have a multiple of its derivative in our integrand. And this is definite. Let's go. We have u as the square root of x, which is x to the 1/2 power. And then du, we have 1/2 x to the minus 1/2 dx. I can rewrite this to where it matches what's in my integral just slightly. We have 1 over 2 square root x dx. You see, in my integral is just 1 over square root of x times dx. You notice this is 2 du. If you're not sure, you can check. Take this line, multiply by 2, and you get exactly this line. So we have done it correctly. Now, it's definite. So let's convert our limits of integration to u limits. When x equals 4, u is the square root of 4, which is 2. When x is 9, u is the square root of 9, which is 3. Oh, I have so much in my substitution box here. That's okay. All right, so now I have an integral. It goes from 2 to 3 of e to the u times 2 du. We have 2 e to the u. That was the simplest part, was integrating 2 e to the u. And we evaluate here. So we have 2e cubed minus 2e squared. Final answer. We have one more in this video, which is integral number 14. I absolutely love this integral. So let's go. Well, if we think about the last one and get some motivation here, we see a function up inside the exponent of e. So this suggests we could try substitution. So instead of calling it u, I'm going to call it y. Let y be 1 over x, which I can write as x to the minus 1. And then dy is minus x to the minus 2 dx. And to make this match a little bit more in my integral, I can write it this way. You will notice I do not have a constant multiple of dy in my integrand. However, let me take a little step to the side. You notice this is 1 over x times e to the 1 over x divided by x squared. Definitely, these are equal. Now, okay, we almost have this, except for the minus sign. We can convert this to something of y. And look, this part we can also convert to something of y. 1 over x is y. So let us take this one step here. We have 1 over x squared handed to us in our integral. This is minus 1 dy. So all of this is my work for substitution. We then have, look at this, we have an integral. We have y, e to the y times minus 1 dy. Maybe I should move this down because I'm going to make my comment. If you stare at this, now we have a product. And so now we need integration by parts. It's one reason I called the substitution step y, because integration by parts also has the letter u in it. So if you follow the LIATE acronym, we have algebraic, let u be y, dv is everything else. I guess I'll keep the minus sign with the dv. That's fine. And we differentiate u. du is dy. And we integrate v. We get minus e to the y. Okay, here we go. uv minus the integral of v du. Let's write it underneath. We have minus y, e to the y. we have minus the integral of minus e to the y dy, which is minus y e to the y plus e to the y plus c. Are we finished? No, we are not, because I need to go back to x, my original variable in this problem. So my final answer is minus 1 over x, e to the 1 over x, plus e to the 1 over x, plus c. Definitely, this question took some thought. Maybe I will color my side work. Well, thank you so much, students. This concludes the second video of our integration practice.